All right, so this video is going to cover basically solid mechanics, kind of the important parts of it. I already made a video like this, but in that video, I completely solved an old exam problem. And it was a great exam problem because it covered basically everything that you learned in the class. But I figured having an exam problem from undergrad on YouTube fully worked out is not very good legally. So I'm here remaking the video without that exam problem. So I guess step one in solid mechanics is to understand what a stress, I'm on the eraser, a stress element is. So let's say you have a beam connected to a wall. A stress element would just be a tiny little chunk of that beam. That's literally it. So what type of things do you do with the stress element? So there are two different types of stresses. There is a normal stress, which has a symbol of that. And there's a shear stress, which has a symbol of tau, shear. Okay, so the reason why I drew the shear stresses, where two of them point up here and two of them point down there, is if this is like a beam, the little stress element isn't supposed to spin around just on its own. So the forces trying to spin it have to cancel out. And they do that by drawing them this way, because this force, or that shear, will cancel out with this shear force, and this one will cancel out with that one. Okay, so two types of stresses are normal and shear. So what are types of normal stress that we could come across? The most basic one is you're just pulling on the beam with a force. And this would create a stress, a normal stress. And the reason why it's normal is because you're just pulling on the beam. This would create a stress with an equation of force over area. This area is just the cross section. So if this is like a tube, it would be like pi r squared. Okay, the second type of stress is same beam on the same wall, although it looks a bit different. Let me draw this out also. It would be a uniform stress, and its profile would look like that. So regardless of the height that you're at, regardless of where you draw the stress element, if you draw it right there, or right in the middle, or right at the top, all three of those stress elements would have the same normal stress pointing this way, the same magnitude of normal stress pointing that way. Okay, so the second type is, let's say you have a moment applied at the end of a beam. So the equation for this one is mc over I. Yeah, I'll explain what that is in a second, but the profile looks like that. So if your stress element is up here on the top half of the beam, it will have a normal stress pointing to the right. But if your stress element is on the bottom half of the beam, it will have a normal stress pointing to the left. If your stress element is right on the middle of the beam, it won't have any normal stress on it. And you can see that, well, okay, so this moment is called M. That's a terrible M. This moment's called M. So that's that. C is essentially the radius. So here you have that distance is C. Here, for this element, C equals 0 because it's right on the neutral axis, or the center line. If you had, let's say, a stress element right at the top, it would have a C equal to, I don't know, let's say this again is a tube. It would have C equals the radius. Which, yeah, so it makes sense that if you have a positive C, so you're on the top half, you'd have a stress pointing that way because this number would be positive. But if you're on the bottom half, so if you're like down here, C would be negative, and then the whole stress would be negative. So you would have stress pointing the other way. And you can combine these two stresses or any other types of stresses. For example, if you had a force pulling out and you also had a moment, so if you had a moment and a force, you would have the two profiles. So you would have that for the force, and you would have that, let me draw it over here, that for the moment, and then if you add them, you would get something like, well, it depends on the magnitudes, but you could get something like that, where instead of it being 0, the stress being 0 on the neutral axis, it's 0 at a lower point. So you would have something like that, maybe. So you can just combine them that way. There's one more type of normal stress, and it is, so here I drew the wall back here and then the beam sticking out of the wall. Now I'm gonna imagine you're a dude right here and you're looking that way. So this is the wall, and it extends like back into the page, I guess. And then the shaft comes right out of the middle of the wall, right at you. This circular shaft comes right out towards you. Okay, so now, what if there's a moment? That's a terrible straight line. What if there's a moment pulling around the center of the shaft? So like, what if you're twisting the beam? That would create a normal stress very similar to this equation. MC over J. By the way, I forgot to say this earlier, but I, for a circular shaft, is pi over 64 times d to the 4th. And J equals 2 times I, like always. If it's a square shaft, I think it's 1/12 length times height cubed. I think that's it. It's something like that. And J just equals 2I. So again, if your stress element is right in the center, because C equals 0, the stress element would feel 0 normal stress. But if it's right on the edge, C would equal the radius, and it would be a positive number. So the stress would be a positive number, and it would be the maximum value. If you're in the middle somewhere, it would be somewhere between those. So this looks like that. And I intentionally drew it such that this corner is outside of the circle, because you're drawing the profile right here. Let me actually redraw it to match the standard I set for myself. Yeah. There we go. Okay. So far, these three have been normal stresses. And then there is one type of shear stress. So, got the beam coming out of the wall again. And now you've got a force that's pulling down vertically. So a stress element inside of here, you might think that it has a normal stress pointed down. It does not. It has a shear stress pointed down, and it does not have any normal stress. And that's kind of because, I'm not going to explain why it's kind of because I don't want to think about it. I just want to show you the math. Okay, and the equation for this, so shear stress is a tau equals FQ over IT. T is the thickness of the beam. I, we know what that is. F, we know what that is. Q is something brand new. So the idea of Q, well, okay, let me draw what the profile looks like first, and then we can talk about Q. So the profile of this stress looks like that. So if your cube is right, or if your stress element's right in the middle, right at the neutral axis, it has the most shear stress. If it's on the edge, it doesn't have any shear stress, which seems a little weird to think about, but that is how the math plays out. And the reason for that is because of Q. So everything else here is a constant. F's a constant, I's a constant, T's a constant. So Q is the thing that's making the profile look like this. So what does Q do? So let's say you've got, again, a circular shaft. So I'm going to draw the circle like right there. So the neutral axis is right in the middle. I know it's kind of sloped, but that's fine. So the equation for Q is y hat prime times a prime, which seems really bizarre, but it's not that bad. So if you're right on the middle, you're evaluating Q right on the middle, it should be a maximum. So what does this mean? So if you're right on the middle, y hat prime is, well, okay, step one, you get to pick either the top half or the bottom half. I'm just going to pick the top half, but you'll get the exact same answer whichever half you pick. So y prime is the weighted average height, I guess. So typically if this distance is r, like this distance is also r, you would think halfway is right at the middle. So right at r over 2. But since it's a circle, if it was a square, that would be the case. Like if it was a square and your central axis is right there and you pick a halfway point, then your y prime would be halfway. So it would be, what would it be? H over 4 if this is H and this is L. It would be halfway, but because this is a circle and there's more, if we draw the halfway line, there's more mass below the halfway line than above it, that can't be it. So this y prime is the line that completely divides the circle by weight, I guess. So in this case, for a circle, it is 4/3 r over pi. That's not r, that's y prime. Okay. And then a prime is the total area of this half circle, which is the whole circle, which is pi r squared over 2. So you just take half of it. So here we get a prime and y prime are both values. So they're both a number. So that's good. We get a number here. Now we're supposed to get 0 on the ends. So let's do an example of that. So if we're, that's not a circle. If we're evaluating it right on the top surface, we get to pick either the top or bottom half. There's nothing on the top half because there's nothing. So we can only pick the bottom half. So where would y prime be? Y prime would be right at y equals 0, right at the neutral axis. So that's where we get the 0 value from. Now a prime would be this whole area of the circle. So it would be pi r squared. But because the y prime is 0, because it's right at the neutral axis, we get 0 for the whole thing. So that's kind of an explanation of how to calculate Q and why the profile looks like this. So those are the 4 main normal and shear stresses. Next is deformation, and then next is Mohr's circle. Okay, so for deformation, I'm kind of rushing through this a bit because I gotta go in an hour. All right, for deformation, the easiest example is, let's say you've got a beam on a wall again, and you're pulling it again with a force. As we mentioned up here, this creates a normal stress of force over area. Now, let's say you're pulling like a thing of rubber. It would expand. It would expand by a little tiny bit, and we're gonna call that distance. I think the word is delta, but that's a symbol for it. We're gonna call that distance delta. So what is the equation for how much something will expand if you pull on it? It is FL over AE. So force, that's this number. L is the original length of the beam. So that length. A is a cross-sectional area, so it could be like pi r squared or whatever. E, they'll give it to you. It's property of the material. So like if you got rubber, it's very flexible. So E would be a very small number because the deformation would be huge. But if you have like metal, E would be a very big number, which will mean the deformation will be tiny. Okay. So that's the first type of deformation. The second type is thermal deformation. So like if you heat something up, it'll expand. And if you cool it down, it'll shrink. So let's say we got a beam and we raise the temperature and it expands. Again, by delta, and the original length is L. It would be L alpha delta T. L, we know that. Delta T, we can know that as well. Alpha, again, is a function of the material. So you just need to know whatever material you have. And you could look this up online or in a book or something. Okay, so what if, oh, I erased too much. What if there's a wall right on this end? So it can't expand, but you heat it up anyways. What would happen? This deformation will be 0, but you're still increasing the temperature. So what will happen? So the answer is, well, I'm going to give you the answer, and then I'm going to give you how I'm going to give you the answer I found online, which is this equals E alpha delta T. So that's instead of expanding, it'll produce a stress. If it expands sufficiently, it won't produce an internal stress. But if you restrict the expansion, it'll produce a stress. So that's the answer. Now, how did I get there? So what you would do is you would plug this into here. So let's do that. When you do that, you get L alpha delta T equals F L A E. L's cancel out. You solve for technically can just multiply this E up, and you end up with F over A equals E alpha delta T, and F over A equals stress. So that's the derivation. So if you restrict its expansion, instead of expanding, it'll produce normal stress inside of it, inside of the beam. Okay, so that's it for that. The last thing is Mohr's circle, which I thought was pretty sick, and I understood it better than other people in the class. So hopefully this explanation is pretty decent. Okay. So let's say you've got a beam. Everything is beams in this class. Let's say, again, you're just pulling it with a force. This will be F over A sort of situation. Draw your little normal stress, or your stress element, and it's got a normal stress on it. Cool. Depending on the type of material, the material could be weaker in a normal stress, or it could be weaker in a shear stress application. So I don't know a good material off the top of my head, but some materials have a really high normal stress tolerance, but a really low shear stress tolerance, and some are the other way around. So you might be saying, we're good. Even if this thing can't resist any shear stress, we're good, because the only stress we have in the system is a normal stress. Well, you're wrong. If you choose to draw the stress element sideways, like 45 degrees sideways, it's a big stress element, what'll end up happening is you'll have a shear stress that looks like this. And it makes sense that the arrows are drawn that way, because here you have, well, you technically have the equal and opposite shear stress on the other side, or normal stress on the other side. And if you're deforming it this way, it makes sense that you draw the shear arrows such that you're also deforming the element that way. Okay, so how can we calculate what the value of the shear is if all we know is the normal stress? We use Mohr's circle, which is sick. Okay. Well, okay, first of all, we have to get our two data points. Our first point is this face. So what's going on that face? We have a stress of a number. Let's say it's 10. Let's say this equals 10. And we have a shear stress of 0. Okay, and what do we have on this top face? So what do we have as our second point? We have a stress equals 0 and a shear stress also equals 0. Cool, how is that helpful? Well, it is helpful when you're plotting the Mohr's circle. So there are two axes. There's normal stress on the x-axis and there's shear stress on the y-axis. So if we plot point 1, we would have a normal stress of 10. So we're out here at 10. X is 10, y is 0. And that's point 1. And if we plot point 2, we're at 0, 0. Cool. That's point 2. So we draw our circle. And now we have our Mohr circle. So how does this help us calculate what the maximum possible shear stress is? So where is the maximum possible shear stress? It is at the top or the bottom, in this case, of the circle. So how do we calculate what that value is going to be? Well, in this example, it's going to be pretty straightforward. We know that the center of the circle, center is 10 plus 0 over 2, which is just 5. And we know that the radius of the circle is also just going to be 5. So the maximum possible shear stress is at 5, 5. And negative 5, 5. Well, what would it be? It would be 5, comma, negative 5. So what does this mean? This means if you start in this orientation, and I'm going to erase this and then redraw it step by step, and you rotate, so you're starting at this orientation, and you rotate it, let's say you rotate it clockwise by 90 degrees. You'd end up on that line with the 5s and the negative 5s. Cool. So what happens if we rotate it 90 degrees? Well, we'll end up with a cube, again a cube, that has, so we rotate point 1 to down here, so this is the new point 1. We rotate point 2 to up there, so that's a new point 2. So point 1 is now, since we rotate it, it's on the bottom, and we got a 5, negative 5. So we get 5, and negative 5 would be, stick your thumb out of the page, and that's positive. So negative, I think it would be this way. Negative, well, the way I drew the arrow, it's a positive 5. And then on the other side, on the top, you rotate it down, so now it's on the right side. You would have also a 5 and a 5. But that doesn't make sense, does it? Because we said the maximum would be at 45 degrees, not at 90 degrees. So the actual way to rotate this is if you rotate something by 90 degrees on the Mohr circle, you rotate the stress element by half of that. So in this case, you rotate the stress element by 45 degrees. So now we rotate this down 45 degrees. So side 1 now becomes down here. So we get 5 and 5, 5 and 5, and then up here we get 5 and 5 as well. And to just draw it out completely the rest of the way, 5, 5, 5, 5. Cool. So yeah, if whatever you do to the Mohr circle, however much you rotate it, you have to divide it by 2 when you're rotating the stress element. You have to divide the angle by 2. Okay, so we can kind of see that we can never get to an orientation where all we have is shear stress. There's always going to be normal stress. The best we can do is up here and down here. So we have to pick a material that withstands a maximum normal stress of 10 and a maximum shear stress of 5, along with a normal shear stress of 5. Along with the normal stress of 5, not a normal shear stress. Okay. I think that's it. Probably sped through the video a little bit, but all the key points are in here. You have 3 types of normal stress: F over A, MC over I, MC over J. You have your 1 type of shear stress, FQ over IT. You have the 2 types of expansion, which is you're pulling it or it's thermally expanding. And then you have Mohr's circle, which is how you can find the maximum normal and shear stress for any situation. Okay. Cool beans.